Steve Jordan is the Santa Clara Valley Chapter Chair of the IEEE Power and Energy and Industry Application Societies, and is presenting today on data centers, which in part is he did run an IEEE event earlier, a few weeks earlier, and that really brought together a number of people about this. Steve is also a member of the Purisima Hills Water District and a board member of the district, and a board member as well, a district representative for BOSCA, the Bay Area Water Supply and Conservation Agency, which is the customer to SFPUC in the peninsula in the South Bay and East Bay. He has over 30 years experience developing new products, growing new businesses, and building competitive advantages. He's had operating roles at WaterCity, Paqet Systems, Fairchild Semi, Mostek, and Poqet Computer, and has worked as well as a strategy consultant with McKinsey Company, R.B. Weber, and his own firm. This is a very interesting topic, so take it away, Steve.
Thank you, Dennis. Well, as Dennis said, we had a seminar. We had about 7 speakers from different parts of the data center world, and I guess I'm going to just jump into it. AI has a big impact on data centers, artificial intelligence, and it's primarily in power and heat. First off, power to the chip is going way up as the CPUs and GPUs that are used, central processing units and graphics processing units, are getting bigger and more powerful. AI wants the highest performance, and the more power you put into the chip, the more heat you have to take out. So data centers need new solutions to remove that heat. In addition, getting the power to the data center is kind of a challenge. They are growing leaps and bounds in how much power they would like, and this is not necessarily available. And you have to build transmission lines, which is not everybody wants one in their backyard, surprisingly enough. So I'll briefly touch on a few solutions: BYOP, bring your own power, and optimizing the location. But in all cases, what we've seen with all the people that are in the data center business, they don't necessarily like to talk about it, but they all want their power to be green. So there's 2 major disruptions underway simultaneously. This is borrowed from Vertiv, one of the presenters, but I thought it was a really telling story. The first is that everybody wants data centers to be decarbonized. Both the people building them and the people using them don't want to have them attached to coal plants, or worse. So, and obviously the companies that are building the most are even more sensitive. Microsoft, Google, Meta, Amazon are all very sensitive to that. And secondly, the AI demand is huge for power. This is just a projection from IDC that globally, the power capacity, I'll translate this to gigawatts, 93.9 gigawatts presently to 216 gigawatts in 5 years, from 2022 to 2027. So that's a pretty big addition. And that's kind of a problem. The people building data centers, as I mentioned, so they want to address the problem. They want to reduce the losses, i.e. increase efficiency. They want everything to be carbon neutral. And to some extent, that'll require hydrogen-powered ecosystems. They also want to be water neutral. I'm not going to cover a lot about water, but most of the people want to be net zero water also, and minimize waste, basically. So basically, the whole process of designing and building data centers just in the last 2 years has changed dramatically. Just a word on the chip power. CPUs, which are the blue dots, have, and this is the high-end CPU from another of our presenters, Cloudflare, but what they use in their servers has gone from, in 5 years or so, or from 2016, has gone from around 100 watts to projected next year 350 to 400 watts. That's for CPUs, central processing units. The NVIDIA GPU chip that is the hot one today is 700 watts. So it's a much larger chip. GPUs can grow rapidly because they get a lot of efficiency by adding more cores. So this is a lot of power that you have to find a way to pull out of a chip. It's not easy to do. And so the technology has had to be developed for how to get that power out. And then in a data center, the CPUs are installed into racks, and the racks tend to be of similar size throughout the data center. But they've typically been, a few years ago, a rack was 10 to 20 kilowatts between all of the servers in that rack. And so you could use computer room air conditioning, so computer room CRAC, raised floors. You would have some air conditioning to cool the air. And then as you added more power, you had to get smarter about that. So you would add cooling to the rear door in the back of the whole rack. And over time, you had to get smarter about that. And now what we're seeing, and basically this is where AI comes into play, is a rack will be 50 kilowatts and more. They have to use liquid cooling to get enough heat pulled out of the server in order to keep the server from melting. So otherwise they wouldn't last very long. So the advent of liquid cooling is what has caused the need for data center design to change dramatically. Just to compare different types of data centers, so AI and then HPC, high performance compute. So AI tends to be one type of compute. High performance is used by people like NASA, who also presented at our seminar, for different types of purposes. But in any case, as these data centers have grown over time, we would have seen a medium data center a few years ago of under 100,000 square feet. 20,000, 100,000 square feet need 5 to 20 megawatts of power to do the building plus the cooling systems. And what's happened is then people like Amazon build huge data centers, so they might need 1 million square feet. They might have well over 10,000 servers, and they might need 20 to 100 megawatts. That's 100 megawatts is similar in scale to what a future small modular nuclear reactor might produce. So it's not a small amount of power by any means. And so you can't just snap your fingers and say, I'd like to build, and can you deliver electricity next week? There's anything over 20 megawatts typically requires the utility to identify the generation capacity and then add transmission capacity and distribution capacity somewhere. And that, again, because nobody wants it in their backyard, that typically requires long lead times, permitting, et cetera. And then the far right AI data centers, there's so much power consumed per server that they don't even need to build out as many servers to get to the 100 megawatt power range. What we're seeing right now is, as a new data center for AI might be 30 to 100 megawatts, they will also install AI servers into existing data centers. They just have to limit their ambitions, and they have to get more power typically. But the key thing is liquid cooling to the chip is required, and then renewable energy they want to be have it all supplied by zero carbon energy. So this slide is sort of shows three types of liquid cooling that can be provided. So it's not all uniform, but fundamentally what happens is whether it's a rear door heat exchanger, you have to then run liquid cooled racks from there to a chiller somewhere in the back of the building. Direct to chip liquid cooling is there's a cold plate that is clamped onto the chip, so you can pull this server in and out without, you don't have to connect pipes. But the cold plate has coolant in it. The coolant circulates to the heat exchanger at the back of the rack, and that's what's used for these high-end graphic processing units that are running AI. And then that coolant goes through a heat exchanger, typically to a water-like coolant that then runs from the server rack to, again, a chiller in the back of the building. That'll be like with an antifreeze-like water or deionized water in that. Hopefully, basically self-contained. You're not exchanging heat with a river out in the back. You're blowing hot air out of the chiller there. At the extreme end, and this is really what supercomputers used, is you immerse the whole chip into a fluid. That's not as common. So I think the revolution that's going on right now in AI data centers is this direct to chip liquid cooling with a cold plate. But in all cases, these require a chiller in the back. So it's not really an air conditioner anymore. It's got water circulating in, and then it blows the hot air out to what they call reject the heat into the atmosphere. So that's the heat problem is changing how data centers are designed. The other problem is, so where do you get the power? So now this is a McKinsey projection, and there's not a lot of reliable projections, but there's a few people that are trying. So this is USA only. What they're saying is 2022, they estimated data centers in the US consuming 17 gigawatts, and that'll double by 2030. So now this is power, not energy. So this is the peak demand that the data centers have. And the reason that it's growing so fast is because of so many of the new data centers that are being built will be AI data centers. In fact, we've had companies that we talked with at our seminar that had designs on the board, and in some cases steel in the ground. And when they realized that the design had to change, they put everything on hold and ripped the steel out of the ground to start over because they were running the wrong design. So I went through the McKinsey estimate of growing from 17 to 30. This is all data centers, AI and regular compute, storage, et cetera. The US EIA forecasts total electric consumption will increase about 1% a year. So this represents almost or a little bit more than the doubling of the total power demand, because they're, at least at the US Energy Agency, they're not expecting total demand to increase by that much. But a lot of people wonder if 1% allows for EVs and building electrification, like Bert was talking about earlier in the day. There's a lot of demand for electricity being added to charge the cars and to get rid of gas in the buildings. So there could be some contention for this. Likewise, globally, now this is energy usage. So we're talking terawatt hours, but they estimate that last year all data centers consumed 340 terawatt hours. So it's a wide range on that. But the projection for AI data centers is to grow in 5 years to 85 to 130 terawatt hours. So that's that's explaining half of the increase in energy for data centers is really coming from AI. So that's what's scary about it. And I think in the early slide I had the total power demand. So the problem is, where do you go for this? And it varies. There are electricity providers who want your business if you want to build a big data center. This is American Electric Power, so this is a Midwest utility. I heard their CEO on a financial show last week say, we want the data centers, and we'll work with you to bring you the power. So I looked at their website, and it agrees with him. I guess that's good that they're singing the same tune. But they claim to have cost competitive rates, and they will build the towers and help you find a site, where you can put it. On the other hand, some places don't want more data centers, and it varies. So just going through these, Maryland puts a knife into data center diesels. So that this is for backup, not for primary power. So a lot of places don't want you to be adding new diesel generators. So the industry has had to come up with a solution for backup. Other places like London, are concerned that they won't have enough power for houses. Singapore is another big market, and they have a moratorium limiting to 80 megawatts per year to 4. So they're choosing winners, basically 4 companies. And the reason is, so Northern Virginia has a huge concentration of data centers. They've had a very inexpensive and renewable power, as well as a tech industry. Beijing is huge also. These are, according to a trade publication, these are estimates of the amount of power being consumed by data centers in the 4 or 5 biggest areas. So Singapore, you can see why they're concerned. Silicon Valley is roughly estimated at 600 megawatts, or 0.6 gigawatts. And then you can see why London is concerned. There's a lot of competition there. So BYOP, we'll get into that in a little bit. It's really a concern that and there's been a lot of press on this. AI could need as much electricity as an entire country. Well, that technically was a small country like Sweden. It's only a third of California. So but there is concern worldwide about this. The largest concentration of data centers in our area, since this is sustainable Silicon Valley, is Silicon Valley Power, which is the Santa Clara municipal utility. They've been very accommodative to data centers, but they can't serve all the data centers that are asking them for power and siting. And data centers consume, according to the city, over half of their electricity. So it's been the place where something like 50 data centers are located, and they're quoting multi-year lead times to basically put up the distribution to get that 20 megawatts or 50 megawatts delivered to you. So there's a lot of consternation about, so what am I going to do? What's an aspiring AI provider going to do to bring you the AI tools that they think you want? So the bring your own power is actually not as crazy as it sounds, because there are fuel cell solutions that are competitively priced with the grid. Bloom Energy is probably the most well-known. Of course, it has to be carbon-free. It turns out that the natural gas fuel cell that Bloom has, it doesn't produce carbon dioxide. It produces water out the door. So it does qualify, even though people don't like the fact that it's using gas. There's probably many more solutions, but the best other one that I've heard is to optimize the location, because when you look at AI, you can divide it into a power intensive part of the operation called training, and a lower power called inferencing. Those are the key steps. So I'll touch on the BYOP. This is a diagram of the Bloom Energy fuel cell solution. This is a 10 megawatt power plant. It's kind of like a football field size, a little bit smaller than a football field, but so you can add 10 megawatt increments if you have enough land, and they will deliver this to you, and you don't have to buy power from the utility. And you can do it on a 5-year contract, meaning that if your provider says that'll be 5 years, then you can put this in the interim. So that's one example. And then another company, Edge Cloud Link, has a hydrogen solution. This is a startup, so there's a lot of new technology in this, but this is what's being demanded in the industry to solve that problem. But as I said, the other alternative is if you break down what is needed for to support an AI data center, you bring gobs of data in, ingest, process, and then train. And the training is what takes a lot of compute power. So you can put that in an AEP territory, or if you have hydro up in the Pacific Northwest, you can put that data center there. And then you put your inferencing, near your customers, which could be in the Midwest, but could also be on the coasts. Anywhere there's a big city, you want to be near the users because you don't want the time delays to be great. So this is the second solution that we suspect that the AI cloud providers will be gravitating toward in order to not have to wait 5 or 10 years to build out, because they're ordering the chips now. So they want to, as the presenter of this, Rebecca Weekly, said, you buy an expensive Ferrari, you don't want to park it in the garage. So they want to use the chips now that they're buying. So that's what I have to say. I guess we should look to see if there's questions.
Well, thank you, Steve. I just put in the chat, reading again an article in the Silicon Valley Voice, which is focused on Santa Clara, and they've given a lot of reporting time to, the issues with data centers and the Silicon Valley Power, the Planning Commission, and the City Council. They estimate that they extrapolate that 82% of Santa Clara's power, the overall electricity, it goes to data centers.
Yeah, that's scary, because I saw that, and I also saw that they were quoted as saying it was 56. So, but that's
right.
Why
so there's okay, well, we could say that's a range, but it's quite interesting, because assume even if it's somewhere in the middle, it's a large majority. And it also, in that article, mentions that there are 6 data centers currently under construction and 15 in planning.
15 in the planning means that they have somebody that wants to build them is planning it, looking for sites, etc. But that doesn't mean that they will get a site. I think what they quoted the CEO as saying was that probably less than half of the ones that are in planning, they will be able to accommodate.
Mm-hmm.
It's not just, they have to get the electricity. They get they're sourced differently than PG&E. So they're coming from federal dams primarily. So because they've had very attractive rates in comparison to PG&E, the bulk of the data centers, certainly in Silicon Valley, are in Santa Clara, not elsewhere, because they have a different and more attractive rate structure. But it's funny, they've been very accommodative. The people wanting to buy from them are not happy, but at the same time, they don't go anywhere else. So, or if they go elsewhere, they have to leave the area and find places, it could be Nevada, could be Indiana, Ohio, where there is, or Pacific Northwest, where there is lower cost power not provided by coal. Though they won't touch that.
Yes. So this, well, it's certainly a very eye-opening aspect here that just from a resource allocation issue and the hotbed. Just imagine, though. I mean,
yeah.
The hotbed.
Yeah, they had to, and for NVIDIA to succeed in selling its AI chips to the industry, they had to develop the cooling technology to make this work. So this whole liquid cooling to the chip, and then going to a heat exchanger in the back of the rack, and then you're running piping of, so you're running coolant from all the boards that are inserted into the server rack. You're running a coolant to the back of the rack, and then a heat exchanger then to edge of the building, where you're again pumping a water-based liquid, and then you're cooling that with lots of fans and air in the back. So they had to develop the whole system for people like Microsoft, or Amazon or others to believe that they could buy these chips. But that revolution seems to be happening as we speak.
Indeed. Well, it's been a somewhat quiet revolution because a lot of the constituent members don't like to talk about it.
Oh yeah, none of them would speak on it, and I think because it's competitive. Also, they don't want to share with their competitors what they're doing.
Yes,
that was the main thing that we got. We had the vendors that supply them speak about this, but obviously, you can't say, well, so and so uses this and so uses that. So, but I thought this would be a useful way to give people a comparison for how this works. And I don't know if AI data centers will be as big as large data centers in number of servers or not, because if they had 100,000 servers, you might have 200 megawatts of power demand, and that's just that's more than a steel factory requires.
Yeah, and everybody thought crypto was going to be a problem. We found a bigger.
Actually, what's happening is some of the places that were doing crypto are converting over to AI data centers, because the same infrastructure, and it was the same chips, NVIDIA chips. So it was, but a similar infrastructure for how do you get the heat away from the chip and ejected, into the environment to help with global warming.
Well, thank you very much for coming and educating on this issue and synthesizing, your seminar. It's a fascinating topic that it impacts the Bay Area for sure, and so certainly the South Bay, and actually even California's grid. So it's important to know about.
Yep. Okay. Well, thank you for inviting me.
Great. Thank you.